We are going to discuss the numerical aperture today. We are going to derive the mathematical equation for the numerical aperture as well. So, we are going to find out the numerical aperture of a light collecting system in fiber optic communication. So basically we find out the numerical aperture of a light collecting system. The numerical aperture is represented by NA. So NA gives you the numerical aperture of a light collecting system. There are two light collecting systems in a fiber optic communication system. So there are two light collecting system in fiber optic communication system. Number one, fiber that collects the light from the source. So this is a light collecting system in the fiber communication system. The fiber collects, you see, the light rays from the source. This is the fiber, and here is the light source. So the light source radiate the energy in the form of a cone, and all the rays or the cone should be collected by the optical fiber. Number two, we have a receiver over here. You see, this is a receiver, and this is a fiber. This is another light collecting system. We know that the receiver collects the light from the fiber. So there are two light collecting systems in a fiber optic communication system. Number one, we know that the fiber receives the light from the source, and number two, we know that the receiver receives or collect the light from the fiber. So we need to find out the numerical aperture of the fiber, and we need to find out the numerical aperture of the receiver as well, right? We need to find out the numerical aperture of these two light collecting systems. So we shall find out the numerical aperture of the fiber as well as the receiver. So in this particular class, we are going to find out the numerical aperture of the receiver. And we know there is a photo detector in the receiver of a fiber optic communication system, which converts the light signal into electrical signal. So this photo detector converts the light signal to the electrical signal. So this is a very important device in the receiver of a fiber optic communication system. It receives the light from the fiber and then it converts this light signal into electrical signal into electrical current. So we are going to find out the numerical aperture of the photo detector. We assume that the photo detector is in the form of a circle with a diameter d. So what we assume over here, we assume that the photo detector is in the form of a circle, and the diameter of the circle is d. So let's say the photo detector of the fiber optic communication system is in the form of a circle of diameter d. So what we want to do, we want to focus a collimated beam of light to the center of the photo detector. What is a collimated beam of light? We know that all the rays of a collimated beam are parallel to one another. So if all the rays of a light beam are parallel to one another, the beam is known as collimated beam. And we want to focus all the rays of this collimated beam to the center of the photo detector. So in order to focus all the rays of this collimated beam to the center of the photo detector, we place this circular photo detector at the focal point of the spherical lens. So we will have to place this photo detector at the focal point of the spherical lens. And the spherical lens focus all the rays of the collimated beam of light to the center of the receiver, to the center of the photo detector. So let us consider the diagram. This is the diagram of this light collecting system. This is the diagram of this light collecting system. You see, these are the rays of the collimated beam of light, right? And this is a spherical lens, and here is the photo detector. This photo detector is in the form of a circle, and you see the diameter of the diameter of the circle is represented by d. The focal length of the spherical lens is represented by f, and this photo detector is located at the focal length of the spherical lens. So the spherical lens focus this collimated beam of light to the focal point. Basically, the focal point is located at the center of the detector. So this spherical lens is used to focus the collimated beam of light to the center of the photo detector, and as we mentioned already, we mentioned earlier that the receiver, that the detector is located at the focal point. If the collimated beam of light makes an angle theta with respect to the axis of the spherical lens. You see, the collimated beam of light makes an angle theta with respect to the axis of the spherical lens. Then the beam is focused to the lower edge of the photodetector. This angle, because of this angle, the collimated beam of light is focused to the lower edge of the photodetector. So this angle is known as the maximum acceptance angle of the receiver. Why? Because if we increase the angle beyond the numerical value of this theta, then the receiver will not be able to receive the light. So theta is known as the maximum acceptance angle of the receiver, or the maximum acceptance angle of the photo detector. So we need to find out the equation for this angle theta. Well, we consider another case. You see, if we increase this angle beyond the numerical value of theta, then the receiver will not receive any light at all. So this is the maximum acceptance angle of the receiver. If we increase the angle beyond this value of theta, the receiver will not receive the light rays, the receiver will not receive any light signal. So we should not increase the angle beyond the maximum value of theta, beyond the maximum acceptance angle, because the receiver will not be able to receive the light rays in that particular case. So what we do, we consider this diagram once again. So we consider the right angle triangle on the right side of the spherical lens in this diagram. Basically, we consider, you see, this triangle. You guys can see the triangle over here. Let me draw the triangle over here. This is the base of the triangle. Here is the perpendicular of the triangle, and here is the hypotenuse of the triangle. The perpendicular of the triangle is d by 2, and the base of the triangle is f, and this angle is equal to theta. So we will consider this right angle triangle in this class, and we will have to find out, you see, the maximum acceptance angle with the help of, you see, this right angle triangle. And once this angle is known, we can find out the numerical aperture of the photo detector. So let us consider this right angle triangle once again. We consider the right angle triangle over here. We consider the right angle triangle over here. This is, let me draw the triangle once again. This is, let me draw it again. This is the base of the triangle. Here is the perpendicular of the triangle, and here is the hypotenuse of the triangle. The perpendicular of the triangle is d by 2. The base of the triangle is f, and the angle of this triangle is theta. So we consider this triangle once again, and we are going to find out this maximum acceptance angle with the help of this right angle triangle. So we know that tangent of this angle will be equal to perpendicular divided by base of the triangle, and we know that perpendicular of the triangle is d, and base of the triangle is perpendicular of the triangle is d by 2, and base of the triangle is f. So we calculate tangent theta with the help of this equation, that is d by 2f, and then we can calculate theta from the first equation. Theta will be equal to tangent inverse d by 2f. So we can calculate the angle with the help of, you see, this particular equation, that is tangent inverse d by 2f. And once the angle is known, then we can calculate the numerical aperture of the photodetector with the help of this equation. The numerical aperture will be equal to n naught into sine of theta. And what is n naught? N naught is the refractive index of the medium between the spherical lens and the photodetector. And we know that the medium between the spherical lens and the photodetector is basically air. Okay, so this is how we calculate the numerical aperture of the photodetector. Similarly, if the maximum acceptance angle of the fiber is known, if the maximum acceptance angle of the fiber is known, we can calculate the numerical aperture of the fiber with the help of this equation as well. The numerical aperture of the fiber will be equal to n naught into sine of theta. We will do a few numerical examples in the upcoming slide. So let us do a numerical question. Let us consider the source radiation cone of the source. So alpha naught of the source radiation cone is 40 degree. We want to feed all the rays of this cone to the optical fiber. We know that the size of this cone is very large and the optical fiber cannot trap all the rays of this cone. So we will have to reduce the size of this cone with the help of a spherical lens. So we use a spherical lens to reduce the size of this cone, and the cone of the image is 10 degree. So we want to reduce the size of the cone in such a way that the half angle of the cone is 10 degree. Okay. So what we do, we calculate the magnification first. So let us calculate the magnification, that will be equal to alpha naught divided by alpha I. So we can calculate the magnification of the spherical lens with the help of these two parameters. And we know alpha naught is 4 and alpha I is 1. So the magnification of this spherical lens will be 4. Now we consider another equation. We know that m, the magnification of the spherical lens, is basically equal to 1 divided by d naught over f minus 1. We know this particular equation. Okay. So we rearrange this equation, and the rearrangement of this equation gives you d naught divided by f minus 1, which is equal to 1 over m. And this equation will give you d naught by f. So d naught by f will be equal to 1 plus 1 over m. So we can calculate d naught by f with the help of this particular equation. We know the value of m. The value of m is 4. So let us put the value of m in this particular equation. If we put the value of m in this particular equation, which is 4, so we get d naught by f, which is equal to 1 plus 1 over 4. And 1 plus 1 over 4 is 1.25. So we have 1.25 d naught by f comes out to be 1.2f. So we can calculate d naught, right? We can calculate d naught. Why? Because d naught will be equal to 1.2 f. So if the focal length of the spherical lens is known, we can calculate the distance between the source and the spherical lens. We can find out the distance between the object and the spherical lens, and the object in this particular case is the source. So let us assume that f is equal to 10 centimeter. If f is 10 centimeter, then d naught will be equal to 1.25 multiplied by 10, and that is 12.5 centimeter. Okay. So d naught will be equal to 12.5 centimeter. Now we know another equation. Let us recall this particular equation. We know that m is basically equal to di divided by d naught. So we can calculate di with the help of this equation as well. Okay. So if you want to calculate di will be equal to m multiplied by d naught, and we put the values. We know that m is 4 in this particular case, d naught is 12.5 centimeter, so it will give you 50 centimeter. So the distance between the image and the spherical lens will be 50 centimeter. If we place the optical fiber at a distance of 50 centimeter from the spherical lens, then this fiber will accept all the rays of this small size cone. So what we do another numerical example now. So let us consider another numerical example. Let's say the diameter of the photodetector is 1 centimeter. This is the diameter of the photodetector, and the focal length of the spherical lens is 1 by 2 centimeter. Okay. So we calculate tangent theta. So tangent theta is equal to d by 2f. We calculate tangent of this angle theta with the help of d by 2f. So let us put the values over here. If we put the values on the right hand side of this equation, so we know that d is 1. We put the value of d the diameter of the circular photodetector, which is 1 centimeter, and we put the value of f, which is 1/2 centimeter. So we get tangent theta, and tangent theta comes out to be 1. So we calculate tangent theta in this particular case, which is 1, and we calculate theta from here. So theta will be equal to tangent inverse 1, and tangent inverse 1 is 45 degree. So the angle, the maximum acceptance angle of the photodetector is 45 degree. So let us find out the numerical aperture of the receiver. The numerical aperture of the receiver will be equal to n naught into sine of theta. So we can calculate the numerical aperture of this photodetector with the help of this particular equation. So let us put the values in this particular equation. If we put the values in this particular equation, n naught is the refractive index of the air, which is 1. Theta is the maximum acceptance angle of the spherical lens, which is 45 degree. So if we put the values in this particular equation, the numerical aperture will be equal to 1 into sine of 45, and sine of 45 is equal to 0.707. I think you guys can check the value of sine of 45 later on, but I think the value is 0.707. So the numerical aperture of the photodetector will be 0.707. This will be the numerical aperture of the photodetector. So thank you so much. Thank you so much.